Hi, this is the last part 3 of the cyber infrastructure, clouds, and HPC discussion I'm doing for the Intelligent Systems Engineering E500 course. And it says a little bit of physics, but that was in part 1, and we're now to part 3. All right, here we are. And in this part, we will mainly discuss the relationships of these various concepts, which you already started to do in the overview of cyber infrastructure at the end of part 2. This discussion will be a little more up to date because that overview came from 2011. All right, so the first point is to note when we discuss cloud computing, it has sort of two types of impact. One is the infrastructure and the sort of business model where you outsource servers, computing, and data and file space, and computing is elastic, scaled up on demand, and utility. Now, you don't invest in hardware, you invest in a service, infrastructure, or as a service. The other interesting feature of clouds is that compared to previous systems, clouds have a much better high-level, application-level software. Previously, people had mainly worked at the low level. There were things like databases, and other tools like that, which had a lot of effort. But there were not a broad range of tools. But now we have from clouds both tools such as MapReduce, Chubby, Bigtable, Dryad, Zookeeper, and these tools are very powerful and typically more powerful than previous tools. In particular, MapReduce is the first of these probably to be broadly studied. It was produced a long time ago, 2004, by Google, Dean at Google. And it is designed for information retrieval and databases to make them parallel in an efficient fashion, but it's excellent for many parts of science data analysis. But there are some parts it doesn't work with because it has relatively high synchronization overheads because it writes everything to disk. And that is addressing this gives you the so-called iterative programming systems, which was Twister was the original one we did, very well-known system, but no longer state-of-the-art. And nowadays, the Spark and Flink are probably the best known and most efficient of these systems. Another key feature of the cloud runtime is the file system. Previously, in HPC systems, you always had some variant of network file system, with Lustre being the one quite commonly used. But now you have the Hadoop file system, Bigtable, where the data is on the computer that's doing the calculations. All right. If we look at how one does scientific computing, we have at least 3 types of systems. Large-scale supercomputers. Actually, they can do everything because they're so powerful. Any possibility is they're so expensive you may not want to use them for problems which are actually the majority, which cannot use their rich features. They have very powerful nodes, multi-core with GPU enhancements, and extremely high performance, low latency, microsecond networks. A very important class of systems are called high throughput. That is illustrated by the so-called European Grid Initiative, or in the US, the Open Science Grid, OSG. And those are aimed at what I call pleasingly parallel jobs. Jobs which run independently and effectively sequentially, although you can have pleasingly parallel, modestly parallel jobs, but typically you have each job is sequential. It's your favorite R program running a data analysis on a single event or something like that. This is very popular because it's very generally used. If you look at say the European Grid Initiative was originally designed for particle physics, where every event produced by the accelerator at CERN or the other accelerators at Bell and other places, they can be analyzed independently. And you only join multiple ones together just to avoid overheads. But there are billions of events, and you just analyze those in a pleasingly parallel fashion by chopping up the events and putting assigning each core independent events. You can do this in a so-called cycle stealing or volunteer computing fashion, where the system steals the computing from idle machines. And as I said, this is all illustrated by LHC data analysis. Condor is the best known such system today, although there have been many others. And in fact, BOINC from Berkeley is a related concept. Like Purdue has a big Condor cluster, and Condor itself comes from Wisconsin. Grids typically run across administrative domains, so they have to use federation, so to allow multiple resources to be used in a loosely coupled fashion. And that federation is non-trivial, and is one of the reasons why grids are quite difficult. There's a huge administrative overhead in sharing systems. The Grid initiative pioneered the use of services, and the concept in clouds is now called software as a service, where you have a capability, which is a service, or nowadays even a microservice, a small service, and that is packaged so that you feed in a message, and out pops a message, which is the answer. Then you need to use these portals and workflow, again pioneered by grids, but are more or less unchanged for clouds. Portals actually give you access to the computing environment, often have features when they're called gateways to allow you special access with ability to specify the parameters of jobs such as molecular dynamics or some genomic analysis. And then workflow allows you to join multiple jobs together when you want to run a pipeline or a more complex network of jobs on a single initial data source. All right, now we come back to something we studied in part 2, clouds, HPC, and grids. We used MPI as the term in part 2. And there's one thing that's worth noticing, which is what we pointed out before, that if you classify system, grids are the least capable because they have the longest latency between the communication and synchronization latency between the components, then clouds, and then high-performance computing systems. So this says that the cloud, almost by definition, can execute a grid workload because they're like a grid, but with better performance. However, clouds may not be able to do HPC applications because they may need low latency. Classic HPC systems are effectively so-called MPI engines, and they offer the highest possible performance on closely coupled problems. There are 4 forms of the basic MapReduce and MPI, and there is a 5th form called map streaming when you come to edge computing. So the first form, which we look at later, is map only, pleasingly parallel. Every job runs independently. Classic MapReduce, which is exemplified by Hadoop. You do a single map on each node, then you do a reduction operation to collect all the information together, and you write that to disk, which gives you very fault tolerance in both for performance and for just faults. The iterative MapReduce is needed when you have iterative problems, because then you can't afford to write the disk because it takes too long. If you're doing some iterative algorithm like expectation maximization, it has lots of reduction operations. But those reduction operations cannot run well in Hadoop because it's not iterative. You need to cache data in memory using in-memory databases and things like that. Spark and Flink do this extremely well, although even there, they still do not use optimized communication primitives. And so they're outperformed, in fact, by Type 4, classic MPI. which has small point-to-point messaging built in, and it is originally developed for simulations, but can be used very effectively for data analytics. As we point out, iterative MapReduce is so-called collective communication. That's where every node is communicating with every other node. That's because there's no nearest neighbor structure in a big data problem. And however, simulations tend to have nearest neighbor structure. And that's where they don't use collectives. They use point-to-point, multiple simultaneous point-to-point operations. Here are these 4 forms, 1 through 4, with the 5th form map streaming. And let's ignore the 6th form, which is shared memory, which is used for cases where the communication overhead of items 3 or 4, when you're communicating between processes, when you need the much faster performance you can get from a shared memory. I've already described these first 4. It's worth looking at the 5th, map streaming. The map streaming has the following architecture, which is worth bearing in mind for edge computing. Data comes in here, stored on brokers. A typical system used is RabbitMQ or ActiveMQ. Those brokers queue the information because you have to have a buffer, because events can come at erratic time intervals, and your computers may not be able to cope with that erratic effect. Then there are maps which are running continuously, and they just grab the data from the queues, process it, and add it to whatever's going on. So that's map streaming. It's a sort of different computing model from map only, where the data comes in here. Each separate data goes to a separate map. All right. So if we look at parallel computing, that is typically done in single program, multiple data. The maps correspond to sharding. You divide the problem up into parts. You divide the weather up into different parts, say, I don't know, 1 kilometer square across the world. And those then you write down the Navier-Stokes equations, or whatever variant you need, and the physics of the atmosphere. And then you will find you need to get good performance, low latency communication with this microsecond latency, and they can use often very large jobs, 100,000, many millions, possibly eventually billions of cores on the same job. And they tend to run in batch mode at 100% utilization. Whereas that compares with clouds, where due to the elasticity, they have to have quite a lot of reserve capacity to be able to scale up on demand. These are reasonably fault fragile, because if one node goes down, and then all the other nodes wait on it, that's different from, say, pleasingly parallel or MapReduce, where there is no fault fragility, because each node, each map runs independently, and then it writes everything to disk. And when it writes to disk, that task is finished. You needn't wait for the other tasks which are not finished. So MapReduce has a huge advantage. It's much less sensitive to stragglers, slow nodes, and everything like that, because once a node is finished, it can be released to the system. Once a task is finished, it can release its core or node to the system, and the system can do what it wants. Then we have MapReduce, of course, has map-only as a special case. Then we need to link HPC to clouds. This is the types 3 and 4 of the MapReduce on the previous slide, where you need memory caching to avoid the overheads of writing to disk. So you could argue that high performance seems natural for high data of high size, which is what big data is. And as big data needs lots of processing, then HPC could do it faster. So what's the cons? Well, the con is that you have I/O. So if all your time is spent reading the data from the disk, then it doesn't really matter what happens to your computing or your floating point operations. If they're done fast, it doesn't matter. The other issue is pleasingly parallel. If the job is pleasingly parallel, like some accelerator processing, then you can run it without using the HPC high-performance network. And I say there are problems like databases, parallel databases, which are essentially map reduce. And again, they don't have the tight synchronization constraints addressed by high-performance computing. Note that Andrew Ng, a very famous Stanford computer scientist, said that all leading machine learning groups must have deep learning and HPC excellence. That's because there are some very important machine learning problems, such as topic modeling, clustering, deep learning, dimensional reduction, graph algorithms, which need these map collective and map point-to-point and benefit from HPC. And you will find MPI is often big factors, 10 to 100 faster than Hadoop, Spark, Flink, and Apache Storm. I've already stressed that exascale simulations, these supercomputers, they're running for differential equation-based models with huge number of sharded points, mesh points, particles, galaxies, stars, and they have to have small space, link space, because of the rapid variation, say in their turbulence. They need small distances between the mesh points, and they need small time steps to get accurate answers. And then you need the large memory and the large compute power of these exascale machines to solve a single or just a few problems. That's called capability computing. Big data problems, on the other hand, do not have the differential operators. They have a different communication structure, and they don't really seem to naturally often give these giant big problems. Rather, they give lots of either small problems, the pleasingly parallel type, or medium problems, where each of them is just large but not super large. Like your deep learning, it might need 4 nodes, each with 4 GPUs. And then you would have a perfectly good deep learning network. And you will now get those today on a modern HPC cloud, such as Baidu and Amazon and so on. So that's because deep learning at the moment tends to mainly use small accelerator enhanced HPC clusters. Notice that even if you have a small cluster, you still need HPC expertise and HPC software. So you really have to actually bite the bullet and learn HPC, and that's why Andrew Ng says any serious machine learning group requires HPC expertise. If you look at these HPC cloud integrated systems from modern vendors, there is, at least if you lose the terminology from IBM, HPC Cloud 2.0 uses DevOps to automate deployment on the cloud or HPC system. And Cloud 3.0 uses software as a service, or maybe now function as a service, to deliver wisdom or insight as a service. And all right, now we come to a little more detailed comparison of data analytics with simulations. We've mentioned several of these differences before, like collective versus point-to-point, nearest neighbor versus full linkage of the points in the simulation. All right, let's just make a few remarks on the overall structure of applications. We've already pointed out the map streaming model, and that really deserves more attention because it's actually well understood how to process streaming data. And it's used ubiquitously in commercial big data, such as Amazon Kinesis, and Google and Microsoft have their own somewhat less exotically named systems. And it's just used. And there's lots of software. Storm and Heron from Apache, which come from Twitter, Google, Millwheel, and so on. And I say Amazon has their own commercial, very application-oriented system. It tends to mainly work, I think, on web clicking. It analyzes all these business transactions on the web. Each of those business clicks gives you an action which you have to process. However, science is way behind here, in my opinion. It is not using these modern technologies. It's using maybe equivalent technologies, but they're by hand. They're not really exploiting modern commercial systems. We pointed out that pleasingly parallel is important in everywhere, both science and commerce. And this corresponds somewhat to the so-called long tail of science, where you have big science like astronomy or particle physics or ocean observatory. And then you have little science like people putting sensors on squirrels and analyzing them, or even groups that doing their genomic sequence analysis distributed fashion across the world. Each of those users is themselves not terribly big, but together they add up to a lot of data. So the long tail, so the big science is like 10,000 users of the Large Hadron Collider. That's big science. 10,000 individual gatherers of squirrel data is long tail science. And this is somewhat related to crowdsourcing and citizen science. If you look at the difference between commerce and science, there are some important differences in algorithms. Search is very important commercially. It's not so important in science because you don't have lots of users of scientific data, just a few. So the need to produce scalable search engines which can have 1 billion simultaneous users is not important. Recommender engines are very important commercially. They're not so important in science. And those have different structure to some of the things that are important in science and commerce, deep learning, clustering, topic models, graph analysis. Note, graph analysis are particularly sensitive to communication and even with microsecond latencies are hard to parallelize. Also, we notice that when we do data analysis, we need to discuss the data and the model separately. Because usually you have, I told you when I was beginning in physics, I produced models. Well, everything has in data has a model. The model could be the SQL query, which implies an entity relationship model, or it could be a particular nearest model for finding the driving the recommender engine to recommend the next movie you should watch. Each of those is a model, and that model is maybe a complex model like latent Dirichlet allocation or clustering. It could be a simple model. But the model has parameters, and the data has values, and the data and the model are often mixed up in discussion. You need to separate them if you really want to get the right answer. Notice the simulations produce big data. They are a source of data. But they also need boundary conditions. When you learned how to do differential equations, you were told they had boundary conditions. And that's actually a relatively small amount of data because it's the boundary data. Whereas the model is the volume, which is bigger than the boundary. If you do things like data assimilation, that is data is assimilated and the model is fitted to the data, and it's fitted, of course, and it's evolved by Navier-Stokes equations. You use pleasingly parallel in all these cases. Both cases are single program, multiple data, and bulk synchronous processing as their basic algorithm. These are terms very familiar from parallel computing. I won't go into them here. You can look them up. MPI jobs are nearly always bulk synchronous processing style, and they're nearly always single program, multiple data. You have lots of parts. Each part is different from the different data and the different model parameters used in each part, but they have the same program. It just gets different answers because it's using different models and different data. Ordinary MapReduce, classic Dean Google MapReduce is a major big data paradigm. It is not so common in simulations. There are some cases where the reduced summarizing pleasingly parallel executions in some Monte Carlo cases, but it's still not it's important but not dominant. Whereas it's probably a dominant component, 50% or some number of commercial big data. In the cases where there is significant communication, it is typically collective. I've stressed that many times, whereas simulations are point-to-point small messages. And that's why we usually call big data the map collective model. And that corresponds to the importance of differential operators for simulation, which leads to nearest neighbor sparsity. And you do get some things like that, but you do PageRank. And some of the algorithms in LDA have the sparsity. It's not usually as clean as differential operator sparsity, but it has sparsity which can be exploited. But some of them don't have sparsity. Here's an example of a sort of amusing analogy. Here's a picture of chemistry with bonds between the components, and here is different types: backbone, disulfide, hydrogen, salt, van der Waals. The van der Waals is the long-range force binding everything together. And here we have Facebook connections, where you have people linked together. Notice that particles have forces and people have forces, and actually mathematically there's a great similarity in the formulations, because when you do optimizations, you're optimizing energy functions in both cases. The energy function over on the left has a differential equation and Newton's laws or Schrodinger's equation describing it. An energy function on the right tends to be much more ad hoc. It doesn't mean it's less important, but it doesn't correspond to fundamental Mother Nature equations. So that's what I say. There are interesting similarities between graph problems and particle simulations. And then the cutoff, if the simulation says a long-range force like Newton's, like gravity, then that's not so interesting, because that's everything talking to everything, which is a common big data scenario, but it has not got the structure that we saw in the previous graph. And these are all map point-to-point problem architectures. I pointed out the long-range force, the gravitational one, is important in simulations and big data. And these are the cases where all points are linked together. These are typically so-called order n-squared algorithms, very time-consuming, because every point links to every other point. And they're clever ideas, so-called fast model ideas, which are described in the National Research Council report on big data analysis. I recommend reading that. And you will find that reference in many of my papers. And then we have this classification, which I mentioned in the last talk of this series, called ogres and diamonds. And they have various facets which describe these things we discussed above, whether it's a long range order n-squared or not. And they do not, however, discuss the underlying hardware. And this aspect of whether, say, many core Xeon Phi or just Xeon versus GPUs are not terribly well understood. And that, I think, deserves further study. It's pretty well understood within simulations, but the comparison between big data and simulation is a little inaccurate in that type of area. So in the case of deep learning, that is block sparse. So you have blocks there. It's sparse because of the linkage of the neural net, but it's blocked because you might have images there and blocks of images. And those blocks are very important because they lead, when you look at the full matrix problems, and we know full matrices make MPI and GPUs run like a hotcake, because there's no latencies. The latencies is minimized. It's interesting that when I do a lot of big data problems, I use conjugate gradient to solve equations. But as there's no sparsity in many of these problems, I use actually classic full matrix conjugate gradient, whereas in HPC and solving simulations, they're actually switching to sparse conjugate gradient because they have a sparse problem. Another interesting feature of simulations have to be high precision because they're differential operators. You're going to do lots of subtractions. You need high accuracy. Whereas big data often don't use high accuracy because the data is not that accurate. So deep learning has been revolutionized by 16 or 32-bit operators. There are no derivatives in big data, and the data has inevitable errors. So it's much more plausible that low accuracy representations will be effective. So if you look at machine learning of the type clustering and things like that, it can benefit from all the HPC style interconnects and the architectures, GPUs, high-speed networks, and so on. But modern clouds have that, and so they're fine. Commodity clouds, the old-fashioned clouds, do not have that. Let's look at the big data requirements. So we have the sort of typical job size. We know large jobs are critical for leading-edge simulations, whereas data analysis tends to be either pleasingly parallel or lots of modestly parallel jobs. As far as I can see, that follows from the event structure of observational or commercial applications. All of these, I mean, good example is the number of image-based problems, pathology, telescopes, light sources all produce images. Those images can be processed possibly by modest-sized parallel jobs, but each of them is then run independently. And then we also sort of stress that the long tail of science produces such pleasingly parallel, lots and lots of small jobs. So that says using HPC machines to analyze data, which is people keep trying to claim is a great idea, is not a trivially good idea because they don't need the interconnect of the same type that is needed for these large simulations. So you should probably use supercomputers to do simulations and use a more commodity cloud-like or HPC cloud-like structure for other jobs, big data jobs. All right. So if you look at HPC, they're using Docker. They're really obsessed by deep learning because it's such an HPC-specific problem. I should point out the original paper on HPC for deep learning was written at Indiana. In fact, I talked to the person, Adam Coates, who did all that work, a brilliant Stanford PhD, who's now on Silicon Valley being very successful with Baidu. And as I've said, the big data uses HPC clusters for deep learning. That's why Andrew Ng said it's so important. If you look at Docker and OpenStack, Docker is typically more interesting to HPC people because Docker is more efficient than OpenStack, and Docker is appropriate for running node-level sharing. If you want to give a single node to a user, which is inevitable if you want to run a parallel job, because you're going to give 100 nodes to the user, or 1 billion nodes, 1,000 nodes, or 1 million nodes to the user. You don't need any core level sharing. However, if you're doing pleasingly parallel processing of events from smartwatches, well, those are core level parallelism, and the sharing at the core level given by OpenStack in a secure fashion is much more useful. However, OpenStack has significant greater complexity and corresponding, it's harder to use, it's harder to get good performance. And so only use OpenStack when OpenStack is necessary, and use Docker or just classic bare metal HPC otherwise. I mean, there are plenty of uses of Spark, Hadoop, Cassandra, HBase in the science community, but it's not broad-based. Languages. Well, there's a rich set of languages. Around 2000, I had a project called Java Grande. It was trying to make Java run fast. You can see actually the sad website which stopped in 2000, largely due to the stock market crash, made these things less exciting. And if you now look at Java, it's actually reasonably efficient compared to C and C++, and you can actually get comparable performance, and we have a paper on that. And Java is typically used in big data, but you can mix quite effectively. Like if you want to use MPI, which is a C or C++ construct, typically you can just bind that to Java in an efficient fashion. Notice that scripting language are hugely important, in fact, of growing importance, but they address different requirements than Java and C++. Scripting language are used for workflow, overall orchestration. Java and C++ are used for the inner kernels, running them flat out. You don't want to make scripting languages run the inner kernels. So if you look at sort of the stacks in clouds, clouds have made this stack here very popular. Network as a service with OpenFlow, infrastructure as a service. This was built before Docker became, well, it says here Docker is getting more important. What isn't here is serverless, which is probably the most important development here. I can't even write it, serverless. You should learn about serverless computing. It's a way of hiding the infrastructure. Then we have platform as a service, such as MapReduce, or if you're doing simulation, Petsy or Saga, those are simulation tools, or compiler tools, or sensor nets. You can produce platform as a service for lots of different applications. And then you finally package the answer for use. And that is done as services, or even software as a service, are large chunks of software. Function as a service are small chunks of software. And the function of a service with microservices buried as functions on serverless platforms are becoming very, very popular. But this concept here of stacks of services going from the network to the computer infrastructure, through the middleware, through the application software is very important. And it's valid everywhere. It was produced for clouds, but it's equally valid for HPC simulations. Here's a very famous old plot I once produced with my student Supun and Judy Chu. We just compiled eventually 350 software packages, after which we got tired. We put them in 21 layers, which are actually pretty effective. And we just gave up at the beginning of 2016 because we got enough. And it illustrated the point. There's richness in all these layers. And you have here, we actually have some open source. That's Apache Big Data Stack. Although not everything is Apache. MongoDB, for example, is not Apache, but there's a fine open source system. By HPC, we put HPC technologies here because our view is we should use HPC to enhance the Apache stack for good performance. Here's another way of presenting it, which Google does. Here are the brilliant Google inventions: Google File System, MapReduce, HBase, which is the same as Bigtable. Dremel is the same as Apache Driller, a way of looking at SQL queries on unstructured data. Pragle, which is the same as Giraffe, which is a way of doing graph computing, which is probably superseded by other techniques. Flume Java is an orchestration approach, which became Apache Crunch. It actually got sort of slightly superseded by Cloud Data Flow, which is Apache Beam. Colossus is a better Google file system. Spanner is a so-called NewSQL database, which was implemented as F1. And then Millwheel is Google's version of Storm and Heron. So notice these are interesting because they show you where Google has found the sweet spots in the critical software components. They're plotted as a function of time. This is a Google slide. I just translated that slide into words so you can read it a bit more easily. And also, I can put down the Apache equivalent. So notice they do not discuss security. Surprisingly, data transfer. Commercial world doesn't do much on data transfer. Scheduling there is Google schedulers, but also there's Yarn and Mesos from Apache are pretty dominant schedulers in the big data world. And I said serverless computing has come along recently. OpenWhisk is the Apache's serverless computing system. All right. Here's another way of looking at exactly the same thing. We have on the right the classic HPC software. Kepler is a workflow system. That compares with Beam or Crunch or Tez as the big data workflow. We have libraries, Mahout versus TensorFlow versus the millions of R and Python libraries. That compares with ScalarPack, Petsy, MATLAB, and so on. High-level programming. Pig, Hive, and Drill are famous. The domain-specific languages are seen in HPC. They're not as popular. Exceed, the big NSF supercomputer environment, has a software stack. That's sort of their version of platform as a service. I don't think it's done as nicely as the big data world does it. Languages, we already discussed that. Java, and SQL, of course, Sparkle for graphs, Python versus Fortran, and there's one language in common. Python is used in big data and HPC. Streaming, there is nothing in as far as I know in HPC. whereas we have Storm, fed by published subscribe, which is Kafka or RabbitMQ and Kinesis. Hadoop is the parallel runtime. Hadoop, MapReduce, and that compares with MPI, OpenMP, OpenCL, CUDA, Exascale runtime. Coordination is Zookeeper. Caching is Memcached. Data manager is HBase, Accumulo, Neo4j for graphs, MySQL for databases. There is some funny data transfer systems, but I don't think that's so commonly used. And in fact, the HPC solution, GridFTP or Globeless Transfer, is probably best. Yarn and Mesos versus Slurm. HDFS and object stores versus Lustre. Formats, Thrift, Protobuf versus HDF. And then we have the OpenStack infrastructure as a service. OpenStack Docker, and I should have put serverless here, versus Linux, bare metal, and SRIOV is a way of getting good performance on OpenStack from modern networks. All right, so we have these different worlds, and HPC Cloud takes the best of Apache and the best of HPC and merges them together. And these are the 21 layers listed. And the only point of the 350 and the 21 is, so there are 21 layers. There's a lot of, I mean, that 21, I mean, it's possibly should be 25 or 18, but it is not 3. There are plenty of layers which are needed. And we don't have to, you can study all the papers we have written on this, which describe the layers and the status of those layers. And what's been useful is the number of layers, which you need to worry about, which is non-trivial. I showed you that for Google, which doesn't list all these layers, but that's just because they haven't got dominant papers published in that. The ones they list are the way they got great papers. And then the amount of software, which seems to be good to reuse this software, 350 is a big number. And the final 3 slides are papers. The first slide is current research. And these are actually papers and other slide decks. We have a big project called Spiral. This is a 21-month report. And the Twisted 2 is our current big project. HARP is another big project from Judy Chu, who she'll tell you about in her talk, which is funded by the same project. And a lot of this is all to do with IoT and serverless computing and streaming data. So that's our current work. If you go a little bit in the past, we have work on, which is actually pretty modern, on big data simulation convergence. I've given you some of the highlights of that effectively. I've given an application analysis developed with NIST. So here's an earlier talk on clouds and cyber infrastructure, and a general discussion, which I actually recently updated for the E534, the big data class. That is a discussion of the data science and the cloud technologies. I've given you this 2011 talk before. That's what we took some slides from in part 2. And here is a talk which is some of my thoughts back in 2007, on comparing parallel computing grids and Web 2.0. Then right in the past, we have parallel computing 27. That was my overview of parallel computing, updated from the work I did in the 80s and 90s. Some of my early work was described in this talk I gave when I first came here. We did lots of work on Web 2.0. That's summarized here. That's where Marlon Pearson now works for UITS. We had a long tutorial. It's quite well. It's all on SlideShare and quite well cited. And this last talk here is one I gave on particle physics. And here I just give you I'm still working in that field. Here's a paper published 25th of August, 2017. And that's it. So that's the end of this presentation on cyber infrastructure, clouds, HPC, and a little bit of physics. Thank you very much. There is another talk, which is a more focused discussion of the Twister 2 project. Thank you very much.